In a previous video, I shared the idea of taking my sound card from my 65816 build and refactoring it to work in my 8286 build. I've done some of that work, and I thought I would share maybe some of the adjustments I've made to the schematic and show you what that PCB is going to look like, and maybe provide a little bit more background about how this is going to hopefully work inside of my 286 system. So real quick, if I look at this existing sound card, that sound card has its own dedicated processor, which I'm just calling an audio coprocessor. And for that, I'm using a 65816 processor. So that processor then has ROM and RAM and address decode logic to go with it on the sound card. And in my previous system, that then plugged into a host system that had its own 65816 processor. Well, I'm going to keep this sound card with the 65816 processor on it as that audio coprocessor, but now I'm going to plug it into a 286 host system. And with that comes some changes. So the 65816 has basically an 8-bit data bus, while the 286 has a 16-bit data bus. So that's the first thing I had to consider is, am I going to use this card as an 8-bit card or as a 16-bit? And I thought I better switch this over to a 16-bit card. So that's one of the sets of changes that I made, is to add support for a 16-bit data bus on the sound card instead of an 8-bit. The other modification I had to make was really just the address decoding for when is the sound card active from the perspective of the 286. And then, of course, to map interrupts. And I am using, maybe I'll just call it bidirectional interrupts at this point. So my sound card can interrupt the 286, and that's what you would expect, that it can interrupt something back and say, can I get the processor's attention? But I also have support that the 286 can interrupt the sound card's processor. Maybe there's things it needs to do immediately, like stop playing some music and play a sound effect, or add a sound effect on top of music that's being played, or whatever it might be. So I just had to make sure I had a way that I think I can map that all out and make that work. So I've done some of these changes, and probably the most significant things, like I said, are really this extra dual port RAM to support a low byte high byte configuration. On the old schematic to the left, I just had a single dual port RAM IC, but as I look to the right, I now have a pair of them. So if I take a look right here, you'll see that there's now a low and a high, and you probably can't read that, and I'll zoom into the actual schematic here after a little bit. But I have a pair now so that I can have the low byte and the high byte. And then I put in some decode logic down here that just simply helps me make sure that the sound card is paying attention to any IO, well, not IO, paying attention to any memory reads or writes from the 286 if it's within the appropriate address range, which I'll talk more about. And then I also had to go in and make sure that I am sending out through the ISA bus the appropriate IRQ signal, and I'll zoom into that here shortly. And vice versa, I have to bring in an IRQ signal from the 286 into the sound card. And on that one, I'm going to kind of cheat a little bit for now, use a temporary solution that I know I'll have to change at some point in the future. And down below, then you can see what this PCB is looking like. So I kind of wedged in this extra dual port IC. Dual port static RAM IC is down here. So I now have a pair of them, along with 6 of these programmable sound generators. I have 3 vias that are going to help control those sound generators, along with give me access to my SD card, and also then give me a couple of debug ports that I can use for example, a 2-line LCD for debugging this sound card, which is essentially a full system on its own. It has a processor, it has the ROM, it has the RAM, it has a VIA. I can plug in an LCD and really do everything I need to. And even if I think about my 286 system, the keyboard, mouse, and all of that, I've moved over to SPI. This card here, all on its own, could also interface with the keyboard, mouse through SPI, since it has native SPI support through a VIA because I'm accessing an SD card. So there's a lot on this card. I have a lot of flexibility of things I can do with it, but at the heart of it, I have a processor. I have its necessary components to make it run. I then have these VIAs that will let me control the sound generators, and those sound generators then will create channels of audio that I bring together and send out through this audio jack right here. And if I talk about the memory space for a minute, here is something that I've shown before, which is my 1 megabyte address space for my 286 system. So I start with a 640K for the RAM. I have the ROM up top, 320K available there. If you've been watching my video card series, where I've left that is at this A0000, and I'm leveraging 64K of memory for my video as far as how I get to the memory on the video card. So basically this is just a window through which I get to the full 2 meg on my video card. And then I've had this space between B0000 up to C0000 that I've left open. Well, what I'm going to do now is basically put the sound card into the first 4K of that. And so to get to the sound card, to work with the sound card from the 286, I'm going to do memory mapped reads and writes. I'm not doing I/O. I'm going to do memory mapped. And I have a pair of those 2K static RAMs, meaning I have 4K. And I'm mapping that to the B0000 through B0FFF. That should be my 1K of memory, or sorry, 4K of memory. That still leaves 60K in that space that I can use for other things in the future. So I still have some room to expand within this memory address space. And if I bring these two up kind of close, scale is probably pretty close on these, so you can kind of see how big my 286 board is compared to the sound card. The sound card is large, as is my video card. Those are both large cards. Now the sound card is going to use IRQ7, so it is going to have to tap into my interrupt controller. So when I look at my system over here, I have this priority interrupt controller down in the corner. And so far I'm using IRQ number 1 for the keyboard, IRQ number 2 for the mouse, and now I'm going to use IRQ number 7 for the sound card. Now that allows this processor on the sound card essentially to get the attention of the 286. I can reverse that though and have the 286 get the attention of the 65816 on the sound card. And to do that, I am basically also setting up an interrupt, but on the 65816 over here through one of these VIAs. And actually, I think I've got that interrupt probably coming in directly to the processor, and we can look at that here shortly if we want. Now, to get that across, I have to somehow figure out how am I going to essentially raise that or trigger that interrupt on the sound card. And I'm going to just leverage one of the unused pins on my ISA slot, and I'll show you that on the schematic. And it's a good temporary solution for what I want to do. Later, though, I do realize I'm probably going to have to change my approach. But I'll talk more about that here when I get the schematic pulled up. So let me do that. I'm going to jump over to the schematic. And so here you see the schematic of my sound card currently. And maybe if I start in the upper left, I have my ISA slot here. And if I just look at the signals that I'm leveraging on this sound card, I need to use all the data lines. So I have 8 data lines here, plus the other 8 data lines. I have my addresses all coming in. I'm going to leverage BHE to help me understand if I'm doing an upper byte write or read versus just the lower byte versus both upper and lower. And then I'm going to use memory read and write. I'm not doing any I/O read and write to this card. It's all done through memory mapped interface. So this mem read and mem write, those active low signals are going to get used to help me with that. I have reset, and then I have IRQ7, which this sound card then can communicate back to the 286 and raise that interrupt. And then I'm going to just repurpose, and this I know is probably going to cause some of you to cringe, but for now I'm going to repurpose DRQ7. That line is where my 286 can bring in and raise an interrupt to the sound card's coprocessor, the 65816. And there might be different lines that I could maybe use here that would make more sense to do that. But I think that's what I'm going to do for now. And at some point in the future, when I do implement DMA support, so I add a DMA controller to my 286, I'll have to change this because I believe these are all DMA related signals. So I'll have to then come in here and remove this signal from that pin and route that signal a different way. And it could just be a little jumper wire that goes from my motherboard to the sound card that gives me that interrupt support, or maybe there's a different pin I would use. But I can be flexible because on my motherboard, the 286 system board, I have a pin header, and I can just simply move that signal to a different pin very easily. And on my sound card, this will be easy enough. If I want to move this off of that pin to something else, I can do that without too much headache. So that's my ISA slot. But then if I scroll down and I take a look, I now have a pair of these static RAMs. This is dual port static RAM. Each is 2K. And then along with that, I've added in appropriate decode logic. And essentially, I'm coming in and looking for this logic here. I need to look for addresses 19 down to 12, those address lines, and they need to match this pattern here. And if it does match that pattern, then I know I'm in this B0000 to B0FFF range. And so I'm just bringing in those signals, inverting the ones that are zeros here so that I can get a high, and then running that into an 8-input NAND. And so there's 8 of those, and that works perfect, that I can run through the 8-input NAND. And out of that, then I have a signal that tells me I'm in the right address space. And then I have an OR here. So if I am in the proper address space, that's an active low, and my A0 is also low, then the output of this signal here is a low. And basically that will then tell this upper chip in my diagram, which is my low byte of memory, to go ahead and be active. And so I will scroll up here so that you can see that. And so that comes up into my chip enable. On what I'm calling the left side or the outside, this goes to the 286 side of things. This over here is my internal sound card side of things. So dual port static RAM. But then the other logic that I have down here is similar, but instead of looking at A0, I look at BHE. And so if I'm in the proper address space, and BHE is low, that tells me it's an upper byte read or write. And then coming out of that is the enable signal for the high IC. And if I'm doing a full 16-bit read and write, I would be at basically allowing both this IC and this IC to be read simultaneously and fill up that 16-bit data bus. So that was the change that got me from an 8-bit to a 16-bit setup. And I need to probably go through and proof this one more time and make sure I didn't transpose anything or miss an update. Those are things I'm notorious for missing, so I'll try to double check that one more time. But that is the memory basically there. And then off to the right, I've got the rest of this that really hasn't changed too much. I do have on my 65816 processor the interrupt line here, which I pull high because when it goes low, that's triggering that interrupt. It is an active low, B for bar, IRQ low. And so this is that signal that I'm going to kind of cheat and take one of those DMA signals on my ISA bus and use that to be able to pull this low. And I think the way I'm going to support that on the 286 is I've got that PSOC, and I do have some available pins, and this is a mess on the schematic. Just play along for a bit here. So I have a lot of signals, plus I have headers hooked up, and there's not a clean way to show that, and maybe I need to get rid of the wires and just show net flags to make this easier to read. But I have a couple of these that I've removed. So I have some free pins on my PSOC. My PSOC already is getting all the appropriate addresses to think about I/O reads and writes. So what I'm going to do essentially is add an I/O address that when I write to that IO address, it really is all managed in the PSOC, and then it'll take that interrupt maybe out of pin P35 and raise the interrupt on the sound card. So short way of saying all that is I'm going to manage the interrupt through an IO read or write, well, an IO write, and my PSOC is really going to be the mechanism to deal with that and get the signal set properly on the ISA bus over to the sound card. And if I zoom back out, here's my ROM and my RAM for that 65816. It's 32K ROM, 32K RAM, which is plenty adequate for what I'm doing here. Above that, I do have some additional logic to maybe just invert the reset signal coming in. The 286 uses an active high, the 65816 system uses an active low, so I've got to change that around. Just some basic inversions of some things here like read-write. This is all to support the read-write logic within my 65816. And then there's some address decode, and I'm going to put all that into a PLD, and that PLD is sitting here. And that really is for within the sound card. When should the ROM be used? When am I accessing one of the vias? When am I accessing the dual port RAM? And when am I accessing the regular RAM within the system? And that logic really shouldn't change from my previous sound card. Nothing on the internal here should have caused a change with that. So I should be able to actually just pop out that PLD out of my existing card, put it into this new one, and that should work fine. This OEB, this output enable bar for DP RAM, I do use that down here in my logic. So if I want to, on the internal side of these dual ports, enable it for the 65816 to read, write, etc., I leverage that signal coming out of the PLD along with the A0 for the sound card. And if it's, a low, then that enables one chip, and if it's high, it enables the other chip. So to the 65816, it doesn't know or care that there's two separate chips here. It's just whether it's an even or an odd address, it'll automatically bounce to one dual port static RAM or the other. And as a reminder, the purpose of that dual port static RAM is from my 286, I can write in commands in a queue in that RAM. For example, say play song 1, play song 3, that type of thing. I can trigger the interrupt, and then the sound card will go read from that queue essentially, and then go ahead and process that command and then clear it out and just have a loop around type of a queue system. And that's worked fine on my previous sound card. I doubt it's bulletproof, and I'll probably get some commentary about there could be concerns with that. Nothing up to this point has caused me any concern with that setup, but I can adjust it as we go. It's flexible, I would say. And then I get up here and I have these three vias, and I have this via down here and half of this via. Those are managing when all of these different sound generator chips are enabled. And so each sound generator has 3 channels essentially. And so if I have 6 of these times 3, I've technically got 18 channels to work with. And this allows me to basically control those 18 channels across the 6 programmable sound generators. And then I have one port on this via that's unused, and I'm just going to take it out to a header. And then I have another via that its only purpose is to manage SPI, and it is managing SPI to this SD card at the moment, and it has a free header. And I did very seriously consider consolidating these two down. If I have a free port here and a free port here, I could just move this down and have one fewer IC, one less on my design. But I wanted to have at least one port that was open for debug purposes. Now I could debug through SPI, so I could send out logging out of SPI. That's a fair argument. But I want to be able to plug an LCD in, and so I have a standard 1602 2-line LCD that I can completely manage off of a single port using, I believe they call it nibble mode, where instead of sending it 8 bits of data, I can send 4 at a time and still control all the other signals on that LCD. So that's my intention. I can plug in one of those LCDs to either of these ports as a debug, and then that still gives me one port to do something else with. Maybe later I'll add in some I/O support, for example, for a joystick or an NES controller. I've got a previous video where I built an interface for an NES controller, so I could easily add that here and plug that controller into this, and then really let the sound card then raise interrupts back to the 286 and process that controller input if I want. So there's plenty of room for expansion on this sound card if I want to down the road. The sound card also has access to the SD card, and then I have this ROM over here. So I have a 0.5 meg ROM. And the sound card, I think I've been using a 64 gig SD card. Obviously, that's way more memory than I'll ever need or touch. I could probably do a 1 gig and still never come close to being able to use it. But those are there. If I have like common sound effects that I'm going to use all the time, I might just put those on the ROM. If I have longer music sequences, I might put those on the SD card. And I can, if it's 64 gig, I can collect as many of those as I want and just keep them on there and not worry about it. I have an oscillator for the 65816. I have an oscillator that drives these sound generators because they need basically a frequency to work off of for everything they're doing. And then ultimately, I take all of the outputs of those 6 programmable sound generators and I bring them together. And basically, they just all tie together. So I'm tying, you can see here, 9 of them together into my right output, 9 of them together into my left output. So I have basically a 9-channel stereo for a total of 18 channels that I can work with. And I may find that I don't use stereo and I just treat this as a mono out. And then in that case, I would have 18 independent channels to do things with. So just depends on if I want to get creative with a stereo type of effect at some point. And I think that would be kind of cool. So I do want to try to play with that and see how I can play with, taking things a little bit out of phase and the effects I can create from a left to right channel. And then, of course, I've got the actual jack that lets me then plug in. Walking through all that really gets me to then this, is what I laid out as the design. And that got me to a photo view that looks like this. And then maybe I'll just go to the 3D view and I can spin this around so you can kind of see what it's looking like. So I do have a ZIF socket here for my storage ROM. I have a ZIF socket here for the 65816's ROM. I'll have RAM then for that. Here's my static RAMs. And I kind of have them spaced out like this just because there are so many signals. And this is always a challenge coming up from this ISA bus. There's so many signals to try to get fanned out or spread out quickly. So I tried to give it space to do that. My processor is sitting here. My decode logic is sitting here. Here's where that PLD sits. And then I have all my vias. My SD card sitting up here along with a header that is all the signals for that SD card. So I've got my 4 SPI signals plus a power and a ground. So if I want to plug in a debugger or something for SPI, I can plug it in right there very easily. And then here's one header for a free port on a VIA. Here's another header for another free port. And then I have really 4 PSGs that I intend to use for music purposes and 2 more PSGs that I intend to use for effects. And of course I can use them all simultaneously. So it could be that I'm playing some background music in a game off of these 4, and then I'm playing the sound effects for the game off of these 2. And I could have left and right sound effects, and so that I could have sound coming from the left, sound coming from the right of the screen, etc. And I suppose even get creative, and as the left and rights come together on the screen, that that sound then plays across both PSGs. So a lot of cool things there that can be done. And then these capacitors and these resistors are part of the output circuitry to get out to this here. And I've got a header there too if I want to use a different type of an output instead of a typical stereo type of jack. And so if I spin this around, you can kind of see what this looks like. Again, with any of these PCBs I'm doing, I know there's a ton of room for improvement. And even on this card, I kind of asked myself, do I want to manually route this or use an auto router? And I leverage an auto router. So I tried to lay out things in a way that made sense. And I've been doing a lot of studying and reading up on PCBs. And it's interesting, even the experts in the field are saying auto router is the route you should go. But the tricky part with auto routers is just making sure all the rules are set up properly. And so that's all stuff I'm playing with along with manual routing. But for this card specifically, I did use the auto router. And the auto router I'm using is this free router. And again, I think it's doing a nice job. It did a nice job on my video card and my 286. I'm perfectly happy with those. But I know there's definitely benefits to do this manually. But even for this card, that manual work would have taken me much, much longer than what I did with the auto router. I think power distribution should be good. I did go with a full millimeter for all power and ground. I went with a larger via for power and ground. And I can see that I've got a pretty good coverage, I think, on the copper fill. So any of the copper fill on the bottom is ground. Any of the copper fill on the top is VCC. And the only area that it might be more thinned out is just down here, just because it's packed full of tracks. And you can see there's a lot of vias down in this. It just gets kind of messy. If I go back to my schematic, that's probably about it. I've got a bunch of filtering capacitors or just capacitors that I put around all the different ICs. I put a pair, which may be overkill, but I have a pair. I typically do a 0.1 and a 0.01 microfarad for every single IC. And then I just have, some additional supplemental caps. There's 4 of them. Sometimes, I typically like to have one down here, here, and here, because that's kind of where power comes in on the ISA slot. It was just too much mess down here. It was causing too many problems. And I do on my ISA slot, if I go back to that for a second and look at it. So this is on my system board, the 286. If I take a look at that, I do have capacitors spread here too. So when these cards are plugged in, they're pretty close to these capacitors here. And I can go with a pretty large capacitor there if I want a bulk type capacitor. And as I add ISA slots to this board, I'll put in more of those capacitors kind of just to follow the ISA slots. I did also on the sound card in the upper left put in a supplemental power connection. I don't think I'm going to need that though. On my video card, I'm finding that the power distribution is working really well, just right through the ISA slot and copper fill, and larger, the 1 millimeter tracks for VCC and ground. But I did add that here in case I want to add supplemental power and connect that into my system board or more into the power connector of the system board. So like any of my schematics and PCBs, I'm sure there's a lot of things that come to mind that I could or should improve here, but this is at least what I'm going to call 1.0 of my 16-bit ISA sound card. So I will get this ordered up and see if I can get it to work from the get-go. So that is where I'm headed with the sound card. And if you have feedback, questions, suggestions, feel free, throw them down below in the YouTube commentary, and I will also have a blog post that just gets into the sound card for my 286, and I'll continue to update that kind of as I go, and I'm working on my sound card. So thanks for following the series if you are, and I hope to see you in the next video.